Hello metallizers, let's do one more integral involving polar logarithm functions in this video. So we have an integral from 0 to 1 ln square 1 minus x ln x by x dx. And the answer is pretty good, it's just minus pi to the power 4 by 180. But the solution development might be a bit messy because the expression you have here is already kind of a mess. But how do we simplify this? Yeah, there should be some ways to simplify and solve. Yeah. So if you try to look into expressions, and if you want, like, try to replace them by alternative expressions for them. So one of the ways can be, let's say, ln of x ln of 1 minus x. This expression over here, like this, can be replaced by from the reflection formula. We know that li2 of x plus li2 of 1 minus x, this is actually Riemann zeta of 2 minus ln of x ln of 1 minus x. Yeah, from here also we can get an expression for ln of x ln of 1 minus x. Yeah, and then we can substitute by Riemann zeta of 2 minus these expressions. Yeah, but that also seems messy because here we have to multiply by ln of 1 minus x and the product of ln of 1 minus x li2 of 1 minus x by x again. That will be a trouble for us. Now some other expressions involving these things. Yeah, one of them is something like this. So we basically have sum from let's say k equals to 1 to infinity of as k by k x to the power k. This expression over here, this is just li2 of x plus 1 by 2 ln square of 1 minus x. So this expression over here, like, this will make our problem simpler in this case, because in our problem we also have ln square 1 minus x. Yeah, so we can replace ln square 1 minus x from the expression that we get from this equation. If you want to grab this equation, like, you can just begin with the sum from k equals to 1 to infinity of as k to the power p x to the power k. So we know that this is actually lip of x by 1 minus x. Yeah, you can start from this and you can easily derive by just dividing by x and integrating. Yeah, and yeah, so in this integral we will use this equation to simplify this expression, and then we will do the integral. Okay, so that will be our goal. Yeah, so we have integral from 0 to 1 or ln of x by x. Yeah, and for the remaining expression we can write this as 2 times sum from k equals to 1 to infinity of h k by k x to the power k. Yeah, and then we have minus li2 of x. Yeah, okay, so is this the expression for ln square 1 minus x? So basically we want over here ln square 1 minus x. Yeah, so take this to the other side and then multiply both sides by 2. Yeah, this is the exact same expression that we get from here for ln square 1 minus x. Yeah, now integrating this thing will not be too hard. Let's see how. So we have 2 times now this is interested in the sum and integral over here. Sum from k equals to 1 to infinity integral from 0 to 1 ln of x by x. Yeah, and then we have as k by k x to the power k. Yeah, again take this integral. If we take this integral for the other expression, we have integral from 0 to 1 ln of x. Yeah, and then li2 of x by x dx. So now you might notice that this will be comparatively easier to deal with than what we had earlier. You might have already noticed that, or if you haven't, you are going to notice in some time. So sum from k equals to 1 to infinity. Yeah, we can take the constants outside. Since the integral is in the world of x, the sk by k, these are just some constant things which we can take outside the integral. We have integral from 0 to 1. This is ln of x to the power k minus 1 dx. Yeah, minus. Now for this one we need to use integration by parts. Let us say ln of x is our u and this other expression is our v. So first of all we just have ln of x and the integral of this thing will be li3 of x. Yeah, of course this goes from 0 to 1. Yeah, and now here's a minus sign, but minus minus it makes it plus, and then integral from 0 to 1, derivative of ln x is 1 by x, and other's integral is li3 of x. Yeah, and we have dx as well. So basically you need to know that here what I used is integral from 0 to x of, let's say, lip of t by t dt. This is actually lip plus 1 of x. So I used this property of Poill logarithms right here. And now for this one we can use just gamma functions. We know that the integral, a modified gamma function, is that integral from 0 to 1 of ln x to the power n x to the power m dx. This expression evaluates to minus 1 to the power n gamma of n plus 1 by m plus 1 to the power n plus 1. Yeah, so using this property or using this result, we can get the following expression over here. Sum from k equals to 1 to infinity sk by k, and then over here this will be minus 1 to the power 1 gamma of 2 by k square. Yeah, and now this expression at 1 also it is 0. At 1 ln of 1 is 0, at 0 ln 3 of 0 is 0. So at both cases it's 0. So just ignore this expression. And now this one will again be li4 of 1. Yeah, basically the same property, the integral of Poill logarithms. Yeah, and here's 1, so that's why that's 1. So li4 of 1. Now okay, so now all of these are actually known expressions. Now I also know how there are some known expressions. Basically this is now minus sum from k equals to 1 to infinity sk by k cube, yeah, plus, and then li4 of 1. Now we know that basically in the Euler sum notation, s of p to the power r times q, this is actually sum from n equals to 1 to infinity Hn of order p raised to power r by n to the power q. This is Euler sum notation. Yeah, and we already have the formulas for the sum in this form. Sum from n equals to n to infinity Hn by n to the power q. So basically these are in the Euler sum notation, sum of 1 comma q. We already have formulas for this type of sum given by Euler himself, which is 1 plus q by 2 Riemann zeta of q plus 1, yeah, minus 1 by 2 sum from k equals to 1 to q minus 2 Riemann zeta of k plus 1 Riemann zeta of q minus k. This is given by Euler, and this is a well-known expression that's helpful in almost all of the cases to evaluate the Poill logarithms integral and series. We'll also use this formula to get the expression. So we basically need q equals to 3 in our case. Yeah, yes. So let's substitute q equals to 3 in this sum. So basically s of 1 comma 3, which is sum from n equals to 1 to infinity s of n by n cube, that is 1 plus 3 by 2 Riemann zeta of 4 minus 1 by 2. Sum goes from k equals to 1 to 3 minus 2 is 1 itself. Riemann zeta of k plus 1 and Riemann zeta of 3 minus k. Nice. So let's evaluate this sum. We get 5 by 2 Riemann zeta of 4 minus 1 by 2 Riemann zeta of 2 Riemann zeta of 2. So basically this is just 5 by 2 Riemann zeta of 4 minus Riemann zeta square 2 by 2. Now let's substitute this value. Substitute this value of the sum over here. 5 by 2 Riemann zeta of 4 minus Riemann zeta square 2 by 2. And if we do that, what we get is minus 5 by 2 Riemann zeta of 4 and then plus Riemann zeta square 2 by 2 plus Riemann zeta square 2 by 2. And we know that Li4 or Lip of 1 is always Riemann zeta p. That's why this is also Riemann zeta of 4. Now it's just some cool arithmetics, just adding and subtracting numbers, which we have been doing since the time immemorial, since our lower grades. So first of all, let's multiply by 2. Yeah, I guess you all know how to multiply by 2. And that gives us minus 5 Riemann zeta of 4 plus Riemann zeta square of 2 and then plus Riemann zeta of 4. Am I doing correct? Okay, no, there's 2. Okay, fine. Now this is minus 3 Riemann zeta of 4 plus Riemann zeta square of 2. Now we know the values for Riemann zeta of 4 and Riemann zeta of 2. Riemann zeta of 4 is basically pi to the power 4 by 90 and Riemann zeta of 2 is equals to pi square by 6 and whole square. Now this is minus pi to the power 4 by 30 plus this is pi to the power 4 by 36. Now I guess you guys know how to take LCM. Yeah, there's LCM is 180 and 30 times 6 is 180, so minus 6 pi to the power 4. 36 times 5 is 180, so 5 pi to the power 4. And finally we get the answer. The answer is minus pi to the power 4 by 180. This is the answer. And this was interesting, right? This was an interesting journey. Yeah. So let's see how we approach this problem. First of all, we try to simplify this integral itself by using the expression we had for ln square 1 minus x. Yeah. Which was basically in terms of a sum and Li2 of x. After using that, we see that we just got like gamma function integral, which we easily dealt with, and other one also wasn't easy if we knew the integral property of full logarithms. After that, we had a classical Euler sum. Let me tell you that this is actually a classical Euler sum formula. This is known as classical Euler sum. And after that, we had to use the classical Euler sum formula, which gave us the following nice result, that sum of Sn by n cube is equals to 5 by 2 zeta 4 minus zeta square 2 by 2. And we just replaced that, we did some mathematics, and we get the answer. So that was it. This was a cool problem, and hope you enjoyed the video. Thanks for watching, and look forward to seeing you in the upcoming videos too.